Alright, in this lecture, we're finally going to talk about the Mobius strip. And I only do this because I find the Mobius strip to be interesting, and we've done so much we might as well discuss it. It covers several topics that we've already done, like the quotient space, and also it really exercises a lot of the things we learned about topology. It's a much harder problem, though. I shouldn't say that. It's not a really difficult problem, but it's the process blends together what we learned about differentiable manifolds and quotient spaces. But we're going to start by defining what we mean by the Mobius strip, and we're going to just jump right in. I'm going to call the Mobius strip, I think I'll call it X, and I hope I don't screw this up and use X for some other things. But X is going to be the real line with the Cartesian product of the open interval from -1 to 1. And it's going to be the quotient space of that in a specific equivalence relation, one that we've seen mostly before. And let me write down what that equivalence relationship is first before I comment on this. The ordered pair S1, T1 is equivalent to the ordered pair S2, T2. And what you can see is this, of course, is the underlying space, and it will be an ordered pair. S will come from all the real numbers. In fact, why don't I give the R the little backbone there. So S will come from all the real numbers, but T comes from this open interval, -1 to 1. That's not a closed interval like the square we did in the last lecture. It's an open interval. And the reason is we want to talk about differentiable manifolds. And so we're going to start from a different place. But this will be true if and only if S2 T2 equals S1 plus 2 pi k and -1 to the k T1. So this is going to be our equivalence relation right here. And it looks very, very familiar to the one we did before, right? The real number part is going to be this, what it amounts to, a circle, right? We've already learned that if we have an equivalence relation on R that takes all points and adds 2 pi times an integer to it, you're ending up with a quotient space on R that is homeomorphic to a circle. But what's interesting about it is that integer k we're going to throw up in the exponent, and it's going to start swapping the sign of T1 if it's even or odd. So this ordered pair T1 and T2, it will be linking not only equivalent places on the circle, right? So S1 and S2 will always be made equivalent by this notion of being the same spot on a circle. But T1 and T2, they will be equivalent if they are equal, right, if k is even, or if they are opposite. And so this part is the new part. And with this equivalence relation, first of all, you can check. So the equivalence classes, right, will be something like if I have S1 and T1, right, the equivalence classes are going to be, will be S1, T1, and then it will be S1 plus 2 pi minus T1, and then it will be S1 plus 4 pi T1, like that, and it'll be plus and minus for all the different k's. So that's what an equivalence class for S1 T1 will actually look like. And it'll be an infinite but countable infinite of points. And so the quotient space we're after is going to have, just like all these other things, it will have a natural projection map, which we'll get in a habit of calling P. Remember, in fiber bundles, the projection map in fiber bundles, we usually use pi, the Greek letter P. But for this, we'll use P. and that's a mapping between R1, between the underlying space, right, and the quotient space, right? So P is that projection. You can check, by the way, that this is an equivalence relation, right? That is important to check, that it's reflexive. Remember, it has to be reflexive, symmetric, and transitive, right? You can check all that, and ultimately, the projection map is going to be, by its own definition, surjective, and it's going to be continuous because we are going to apply T of x with the quotient topology. So we know that that's continuous, which, by the way, means the same thing as continuity always means. P inverse, right, of an open set is an element of the topology of R cross minus 1, 1. So I guess, so that's sort of the definition of the quotient topology, right? That, or if of the continuity of P, it's designed to be such that the inverse of P takes open sets. If this is this, O is an element of the topology of X. Right? If O is an element of the topology of X, the inverse P, the inverse or the preimage of O under P is an element of the topology of the underlying set that we're dealing with. You might ask, well, how do we topologize the underlying set? Well, there we use what's called the product topology, where we take any set that's in the topology of R, which uses the standard topology, right? Which is the balls, which has a base of the balls. So we give the standard topology to R, and for here, for the interval also has the standard topology, right? So they both have the standard topology of open balls, and then the overall underlying set, this thing here, will take the product topology. Which is just all the sets that have open sets here and open sets here, the Cartesian product of all those sets. So that allows us to talk about the preimage of O being a member of the topology of this. So that's where we will begin. We'll use the quotient topology, and then we're going to work from there, and we're going to try to prove, we're going to try to show that this object here is a manifold, right? That's our goal. Our goal isn't, by the way, this is the Mobius strip, right? This space is the Mobius strip. So there is a proof out there, just like the one for the cylinder, where we take this object here, and we take the quotient space, and we take a parameterization of the Mobius strip, and we use all of the same techniques. It's exactly the same proof. It's just a little trickier because the parameterization of a Mobius strip sitting out there in space, it's easy to parameterize a cylinder with cosine and sine. Mobius strip, it's a little bit messier, but it's a beautiful parameterization. If we have time, I'll show you the parameterization of the Mobius strip, but you can look it up. It's very easy to find. But you can do the same thing and show that this is homeomorphic. And you use the same tricks, too. I shouldn't say tricks, you use the same theorems. In particular, in the end, you use this theorem of, well, there is a problem, right? This isn't compact. This is no longer compact, right? So you actually have to probably prove all of the actual inverse functions in that case. But regardless, this is how we're defining the Mobius strip right now. So let's sketch out the underlying space, R cross -1 to 1. The underlying space is going to kind of look like this, right? You might consider that line to be 1, and this line to be -1, and I leave it open because, and this line would be 0, so we call that 0, 1, -1, and of course in this direction we have the real numbers, so that would be 0, 1, 2, -1, -2, etc., etc. So this is sort of a schematic picture of R cross 1, which of course is still a subset of R2, which is defined as R Cartesian R. So that is a picture of this underlying space. And we can borrow everything we learned from, I guess, a couple lectures ago when we did this equivalence relation on just R alone, where we equated all the points that were integers apart, right? We're going to do the same thing here. These every point that's an integer apart, and this R sort of becomes a circle, but this T only flips in sign using this particular equivalence relation we're using now. But we're going to now introduce a few other functions, and these functions we're going to call phi sub k. And phi sub k is going to be a function that maps R cross -1 to 1 into itself, right? So it's not a projection map, it's not a quotient map, it just maps the function into itself. And the way it does it is phi of k will take s and t, and it will give back s plus 2 pi times k, and it will give back -1 to the k t. So there's a whole family of these functions, right? These functions are all indexed by k. So, for example, we have phi of 0. So phi of 0 of s of t returns s and t. Phi of 1 of s and t returns s plus 2 pi and minus t. Phi of 2, phi sub 2 of s of t is going to return s plus 4 pi and t. Likewise, you'll have the negative ones. You'll have phi -1, phi -2, etc. So there's an infinite number of these phi's, and they're all indexed by this integer k, and k shows up in the formulation of how phi returns things as a function. So if you look at these phi's, in particular, say, just look at the general one, what you notice is that it's going to take, the odd ones are going to take points in R1 like this, move them k integer units forward, and flip the sign of t depending on whether you've moved it an even number forward or an odd number forward, right? So if, for example, phi 2 would take 1 at -2, bring this point to 0, and it wouldn't flip it. It would leave it right there. So it'll just take that point and move it there. Phi 3 would take that point, move it there, and flip it. So it would kind of take this point and move it to there. Phi 4 would move it to here. Phi 5 would move it to here. Phi 6 would move it to there. So all of these, so we can almost imagine would take a region like this, right? And then it would move that region an integer number of integers over, and say it moved it 2, then it would move that region to here. If it moved it 3, it would move that region to here, depending. This is what phi 2 would do, this is what phi 3 would do. Likewise, phi -1 would move it, say, to here, right? That would be phi -1, right? So it doesn't take too much intuition to appreciate the fact that these phi's, each one of these phi's, will move regions, all regions, in the same exact way. And since this is an infinite strip, it'll just shift points from here to here. It'll shift every point up to and flip it or not. And therefore, each of these are going to be continuous, right? They're continuous because their inverses are will take, so open sets, right? If I have an open set here, the inverse is simply going to move the open set back, and which is still an open set. So the inverse takes open sets and brings it back to open sets. That's pretty obvious. It can be proven rigorously, but we're not going to. But the inverse is continuous. The inverse takes open sets and maps it to open sets. So the inverse is open, therefore the function itself is continuous. And it's one-to-one, every point will only go to one place, and it's on two in the sense that if you did this for the whole strip would shift, and these functions move everything in one-to-one correspondence along one-to-one and onto way. So this is continuous and it's bijective, right? And without rigorously showing it, I want you to understand that each of the phis, phi k, is homeomorphism. And so continuous and bijective is important, right? So we can show, to show the, bicontinuous, right? It's bicontinuous because phi k and phi k inverse are both continuous, right? Because phi also takes open sets and moves them to open sets. So if phi takes open sets, moves into open sets, and phi inverse takes open sets, moves it to open sets, it's bicontinuous, and therefore bicontinuous, bijective, it's a homeomorphism. So all these phis that we've identified are homeomorphisms. And so with that in mind, we will move to the next, studying the various projection maps, or the projection map. So I'm going to now redraw our strip. Each time I redraw it, I feel like I understand it a little better. I don't know if you guys feel that way, but these pictures are, in this case, we can actually draw pictures, right? In higher dimensions, it gets really impossible to do that. But so here's the here is our underlying space, right? From which the quotient map operates from this space to the quotient space. And then I'll draw something here called the quotient space, make it look like that. And this is R cross minus 1, 1 by the equivalence relationship that we discussed in the last page, right? This thing up here is R Cartesian minus 1, 1. Note, remember, it's an open region. That's why I put dotted lines here, right? Because it's open, unlike the square we did in the last lecture, which was closed. And remember how important being closed was in those proofs, right? Because the continuous image of a compact set was compact, and then a compact set in a Hausdorff space is closed, and we started with a closed space, so which was compact because we knew it was a closed space in a, it was very important that it be closed. In this case, it's important that it be open because we want to show that this is a manifold. So we're going to have the usual topology in this direction and the usual topology in that direction, which is going to mean that sets that look like this, well, let me do little dotted lines just to remind us that it's open. Those sets that look like that are going to be open, right? That they're going to be open in the product topology of this guy. Remember, this has the product topology, right? By the way, if you forget these words, right? We discussed product topology somewhere, but it was just an introduction concept. You can look this up very quickly and see what the product topology means. It's not hard to learn. Once you feel unafraid of checking these things out, if you're learning all your topology from these lectures, you're not going to know it very, very well. But have no fear to just check it out, read up on it, and you'll see the product topology of a product space takes the topology of that and has Cartesian products with the topology of this, and it's going to yield things that will look like open regions on R2. So now, so we take this one little open set. It's one little open set in the underlying space, and I'm going to map that set to. I'm going to map that set into the quotient space. And that mapping is going to give me, I'll try to draw it this way, right? It's going to give me the equivalence class of all the points inside. It's going to give me the union of the equivalence class of all the points inside this open set. So the way I'm going to choose to do it is I draw the open set here, and then these brackets mean the equivalence class, right? So the equivalence class of this open set, what I'm really trying to write down is I'm trying to write down the set, so I take a point in that set, the equivalence class of one of the points, A, and then the equivalence class of another point, B, etc., etc., etc. The problem is I need A, B, C. I need all the points that are elements of that little region. And it's not countable, right? So when I draw it this way, it kind of looks countable. So this is really not a good way of looking at it. But I'm trying to say we're taking the union. So maybe I should do it this way. The union of the equivalence class of A for every point A, which is in the element of O, and if I name this set O, I guess, or I guess to be a little bit consistent with the more whimsical way I'm doing it, I would just do A as an element of, and I'd draw a little set there maybe. But that union of all those equivalence classes, that's what this is P, that's what P of O means, or in the whimsical way, I guess, P of that set, which is defined as P of O, which equals the union of all A and P, the union of all those equivalence classes. Okay, so that's how P would work. Let me write P in red just to. Okay, so that's how the projection map works, right? The projection map, the natural projection map it's natural because it's the only one we can choose. It takes objects in the underlying state and maps them to a set of all the equivalence classes, which is the definition of what a quotient space is. So we've got that. Now let's think, what does P inverse look like though? P inverse is actually pretty interesting. I think I'll do P inverse in green. P inverse will take that equivalence class, but it maps it not just to this little space, it maps it to it maps it to the union of all the points that are representative of that class. So it's going to map it to there, but it's also going to map it to there, and to there, to there, to there, let's see, and to there, and to there, and to there. It's the union of all of these things, right? Because now you're dealing with something, you're saying, oh, I only have one point in here, which is, well, I have one region in here, which is the equivalence class of this region. And so if I inverse map it, I've got to get all of the representatives of that equivalence class. So this map does not just go back to the place where we started with O, it actually goes back to all of these, right? So how might we write that down? And what does that tell us? Well, let's see. The way we would write that down is, so what am I interested in? I'm interested in the inverse mapping under the natural projection map of the, I am going to use the letter O. I'm going to stay with O, right? So this is what I just did. I took O and used the natural projection mapping and got this element, this region. It's not really an element because remember, there's a lot of points in here, so it's a region in this space. I got this region in this space, which I've described as the equivalence class of a region up here, right? But that's really, I'm really struggling to say the obvious, which is that is P of O, right? That's what this is. So, but then I take P of O and I run it through the inverse mapping, right? I run it through the inverse mapping, and I get all of these things. So that's what this is. This is the inverse mapping of the mapping. And normally you would say, oh, I'm doing the inverse of P. Well, this should just give me O again, right? Because I'm inverting what I just did. But clearly that's not what happens. The inverse of a function and the function are not always simply related like that. Because the inverse of an equivalence class is all of this stuff. And P on one of them is the same region where if I did P on this one, I would get the same region. If I did P on that one, I would get the same region. But the inverse gives me all of them. So this is actually the union, right? It's the union of K as an element of the integers of phi K on O. right? This is why we introduced the phi k's, is so I could kind of explain what this thing looks like. The phi k's will take, for every k is an integer, I'll take this and I'll get that set. Then I take the union. Then I get that set. And I take the union. I take that set and I get the union. I do this forever and ever and ever. And the union of all of that together is this, which is exactly what this process gives you. So I start with one open set, dive into the equivalence class of that set in the quotient space. But when I come back out, I'm actually landing in all of these places, right? Like that. I like doing it this way. This is all P inverse on that one equivalence class set, including the one that we started with. And the way that looks mathematically is just like this, right? Just like this. All right, so what can I learn from this? Well, these are homeomorphisms. So these take open sets in the underlying space and gives us open sets. In each k gives us another open set. So this is open. Each one of these is an open set in this topological space. I keep calling it the underlying topological space. I think that's fair because the quotient space is derived from it, right? So the union of open sets, despite the fact that it's infinite, right? The infinite union of open sets is open, right? So we know that this, oops, let me go back to black. We know that this is open. And of course, if the right side of an equation is open, so is the left. So this is open. Well, now we understand that we're using the product, or not the product, we are using the quotient topology, right? Quotient topology. Well, what does the quotient topology tell us? The quotient topology tells us that if we have an open set in the underlying space, its preimage must be open, right? Its preimage must be open. So this tells us that if this thing is open, PO, this thing must also be open, right, by the quotient topology. So from this we learn that the projection of an open set is an element of the topology of the quotient space, right? So this is open. It's open in, I guess, what did we decide to call this? X, right? Open. It's open in X. And PO, I'll try to restate it again, PO is open in the quotient space because its preimage is open in the underlying space. And the quotient topology, by definition, that is the quotient topology. So once we assert the quotient topology for this, we end up with that fact. So this is actually looking pretty good in some ways because what do we have? We know that P is continuous, right? By definition, the quotient topology makes it so. And we've proven, because of the nature of the particular equivalence relation we're using, we've proven that P inverse is continuous as well because because P takes open sets and gives us open sets. So that means P inverse is continuous. So we have a function now. So we can write down that, let's see, where will I write it down? I'll write it down here in green. We have P is bicontinuous, which is nice, and it is surjective, right? So it's surjective because this whole space is covered. It's one-to-one correspondence it only contains equivalence classes, and every equivalence class will be representative. I mean, the whole nature of a quotient space is that it will be surjective. So P is bicontinuous and surjective, but it's obviously not injective, right? It is definitely many to one. I could take P on this and I get the same set as if I take P on that, I get the same set. I take P on that, I get the same set. If I take P on this union of all of them, this infinite union, I get the same single set down here. So it's infinity to one, right? It's non-injective, not injective. In fact, it's infinity to one. So it fails to be injective in the worst possible way. So P is not a homeomorphism. Despite the fact that it's bicontinuous, it's surjective, it's just not bijective. So, it doesn't have to be a homeomorphism. I mean, it turned out in the Mobius strip case, P wasn't a homeomorphism either. P was 2 to 1. It failed. This failing to be injective is sort of indicative of this whole process. And turning things into the quotient topology is what helped us get it to be a mapping between. Remember, ultimately, in the case of the cylinder, we wanted a mapping between this space and the parameterization of the cylinder, right? We're going for something a little different here, but this process of being not injective is just typical of these problems. Now, so what is our next step? Well, we want to show that this is a manifold. We want to show this is a manifold, which means we have to create an atlas and we have to create charts. To create a manifold, we have to prove there's an atlas, and then we have to prove there's an atlas, we have to prove charts. And then to prove that it's a differentiable manifold, we have to talk about the transition functions. And that seems like a lot to do, and indeed it's not easy, but I want to show that this thing is a manifold, and I'm going to work through the entirety of the proof. So we're going to go to yet another slide to do that. And as before, we will start by redrawing. But with this time we're going to redraw it twice. And I don't need as much room. And I'm not going to relabel everything, but I'm going to also redraw it down here. So I'm going to sort of create 2 copies of this thing. Because remember, we're going for manifolds now. So manifolds are charts that map onto, this is essentially R2, right? It's not the whole plane would be R2, and then the part that we like is a little subset of R2. So R2 in general, but it's still R. We're only looking at this part, right? And the same is true up here, right? This is still, I'll write, let's see, how will I write? I'll write it's a subset of R2. And that's important because we're dealing with manifolds, right? So we need to be mapping into Euclidean space, right? Okay, so then we have our set, right? So our set will lie here, and this set is going to be R cross minus 1 to 1 by the equivalence relation. So that's going to be X, set X. Okay, and now though, I'm going to, let's see, I'm going to choose, instead of all of R2, right, I'm going to take out just one region that has a representative of almost every member of the equivalence class. And that region is going to start at, let's see, it's going to start at, say, whoops, I'll give myself some more room. This will be -1, and then this will be 1, and the region I'm going to take is going to be, let's do it in red, it's going to be here. And I'm giving it dotted lines because I'm not including -1 or 1, right? So it's actually going to be the region -1 to 1 cross -1 to 1, like that. And then down here, I'm going to take a different region, and it's going to be, I'll do this one in green, 0 to 2. So that's 0 and then 2. And again, it's going to be, so here it's going to be 0 to 2 cross -1 to 1, like that. And these two regions do not include their boundary, right? So inside here, there is a representative of every equivalence class, except in this case, the equivalence class connected to -1 and 1 is not in here. Well, there's no representative of that equivalence class in here, and here there's no representative of the equivalence class 0 and 2 associated with 0 and 2 pi, or the integer 0 and the integer 2. Let me see. Why do I feel some doubt here? Let me see if I've got this right. If the point 1, the point at -1, it's equivalent to it plus 2 pi, but 1 is not inside this region, and neither is positive 1. So the 2 pi addition, it's not inside this region. Likewise, this minus 2 pi would be well outside the region. So there's no representative in this region for these points. There's no the equivalence class related to. So how do we say that? The equivalence class of 1, which by the way is the same as the equivalence class of -1. So I could write that -1. They're both the same, right? All you need is a representative of the equivalence class inside the brackets to capture the whole class. So this captures the same class as this. So those are the same way of writing. So the equivalence class of 1 is definitely in this set, but there's no representative of that equivalence class in this region right here. Okay. Likewise, here there is the equivalence class of 0 is definitely inside our quotient space, but there's no representative of that equivalence class in this region here. Okay, so however, there is a representative of this equivalence class in this region, right? There it is. It just boom maps. P will map it directly to there, and likewise, if I include 1 here, there's clearly this equivalence class is represented in this region by the projection mapping P. We'll take it directly from there to there. So the important point, okay, so that's exactly the way I want it. So now this region here, I guess we're going to give it a name. We're going to call it V1, right? That's going to be that region. And this one down here we'll call V2. So V2 is going to be 0, 2, Cartesian, -1, 1, like that. So V1 and V2 are two regions inside of the underlying space, and they will have projection mappings to two sets inside the quotient space. And I'm going to call those projection mappings U1 and 2, right? And I guess I should give them, all right, let me make sure we do this well. I want to keep this color coding. I think the color coding will help. So V2 is 0, 2, cross, -1, and 1. So there will be a region in here, and it will be called U2. And then there will be a region in here, which will be called U1. And U1 is simply the projection map of V1, and U2 is simply the projection map of V2, like that. So I've indicated them to be overlapping because, of course, they do share almost every point in common, right? The only thing that this set has that this set doesn't is the equivalence class for, let's see, for 1, right? So here, the equivalence class for 1 lies in that set, and in this set, the equivalence class for 0 lies in this set, but not in that set. In fact, it turns out that despite the fact that I've only showed partial overlap by my drawing here, these are the only 2 points that lie outside of each other. They share every other point. So maybe perhaps a better way to have drawn that would have been something like this. Like that, and then the other one overlaps like that. And inside the blue, inside this red part, you have 0, and then inside this little bump here, you have 1. Right? That's actually probably a better way to to indicate what's actually happening here. But but we'll just leave it abstract for now. A little bit more abstract. Just understand the only thing that they don't share are these 2 equivalence classes. Okay, so why did we go to all this trouble to set up these 2 regions? Well, now I want to look back at how P operates. And P, if I take P and I restrict it, that's what this little symbol means, P restricted to V1, right? Remember, the problem with P being injective was that I could go to all these different places and I get these many-to-one mappings. But if I say, no, I'm not going to allow myself to do that. I'm taking a function. It's a different function. It's not the function P. It's the function P but restricted just to this domain. So the function doesn't work out here, right? The function will never work out here. Now P will work out here, but P restricted to V1, it's not allowed to, and it doesn't. But suddenly, if I do that, all of a sudden P restricted to V1 is, in fact, injective. So P restricted to V1 is going to be bijective and bicontinuous, because we showed that P was bicontinuous already. So P restricted to V1 actually is a homeomorphism. And it's a mapping. So and so how I'm running out of a little bit of space here. Let me think about what I want to do. I think I'll move it over a little bit. And I want to say that P restricted to V1 is a mapping from V1 to U1, right? So I have basically a homeomorphic mapping, right? I have a homeomorphic mapping from a region in R2 to a region in the Mobius strip. This is what I'm calling the Mobius strip. I have a region in the Mobius strip. That's a homeomorphic mapping this way, right? Well, I shouldn't even say this way. Homeomorphic mappings go both ways, right? The inverse is also going to be, if this is a homeomorphic mapping, it's basically bijective and bicontinuous, so it's symmetric in both directions. So this region here, under this restriction, will give me this region here. It's not under P inverse, it's under P restricted to V inverse, so it goes back into this very same region. And likewise, this whole thing makes exact same sense down here. P restricted to V2 is a map from V2 to U2, and it's also a homeomorphism. Okay? So now, and that would be this thing here, P restricted to V2. But now all I have to do is turn this on its head, and I get what I need for a manifold. Remember, for a manifold, what we need are charts. Now, if we're trying to prove that this thing is a manifold, remember, I need charts from here to Euclidean space. They have to be locally Euclidean, right? So I need open sets in here, and I need, or regions in here, right? And those regions need to have maps this way. But these maps will do just fine because they're homeomorphisms, right? They go both directions. So if I take the inverse of these two maps, that will produce the chart mapping on these two sets. So I can create a chart here, which would be U2 P inverse restricted to V2. There's a chart. And then the other chart is U1 P inverse V1. That's a chart too. And it turns out, if you look, it doesn't take too much to see, that every equivalence class that may exist in this quotient space has a representative in this region or this region, and this region. If I take these two regions together, right, if I take the union of these two regions, I get a representative for every equivalence class, and therefore I capture every equivalence class. So the reason that's important is because if I take the set of these two charts, they cover the entire quotient space, which means these two charts are an atlas for the quotient space. So I've created an atlas for the quotient space by doing this. And these are my two Euclidean spaces here, right? This is Euclidean space and this is Euclidean space. Because remember, they're just, although that we wrote them like this, that is a subset of R2, a subset of R2, right? This is a subset of R2. So, oops. So this is Euclidean space, and this is the atlas. So we've created this atlas. So we definitely now know that at a minimum we have a topological manifold, right? Because we have an atlas, and we have an atlas, right? So we have a topological manifold. So I have proven that the Mobius strip is at a minimum a topological manifold. So now the question is the Mobius strip a differentiable manifold? So to address that, we will now focus our attention the other way. We have our core set. Actually, you know what? The way we should draw this, I think, is we should draw this like this, right? And the idea being that we're going to put 0 in one of these little bumps, and the equivalence class for 1 in the other little bump, right? And this will allow us to call this section here U1 intersection U2, right? Where the parts that don't intersect are actually sort of floating out there. But ultimately, what I've drawn here actually is R cross -1, 1 by the equivalent. That is the quotient space, right? The quotient space literally looks, can be credibly shown this way. It has all the points. Inside here is almost every the equivalence class for almost every one of the points in this Mobius in the strip, and the 2 points that aren't shared by U1 intersection U2 are out here. And let's see, I think if I remember right, the way we did this, U2 contain that point and U1 contain that point. Let me just double check. U1 contained 0 and U2 contained 1. U1, okay, so I got it wrong. So this is U1 contains 0 and U2 contain 1. Okay, so that is our Mobius strip, or our quotient space. So now we have these mappings to Euclidean space. So remember how we did that before, is we kind of would draw these little axes. But this time we'll just draw the segment that we knew about, right? So this mapping to back this way, right, was P restricted to V1 inverse, right? And this mapping going down here to this piece of Euclidean space is P restricted to V2 inverse, right? And these are our charts. And these are our charts that go into Euclidean space. And where we keep in mind that this strip, of course, is actually Euclidean space. So now we have these charts. So now, of course, in order to check that we have a differentiable manifold, we're interested in these mappings between these two spaces. So it gets a little cleaner to change the name of these things because now the maps are these inverse functions, right? So we just rename them, right? It's not a problem. We're going to call this kappa 2, and we'll call this kappa 1, right? So kappa 1 equals P, well here, kappa I equals P inverse restricted to VI, okay? So now I had to redraw this. It was just getting a little too messy and I couldn't get my work. I needed more space to do the work. So I've redrawn this. This is U1 intersection U2 inside of the Mobius strip, right? So this is all X here. And I've kind of shown that the representative of U1, or the representative of the equivalence class represented by 1, with 1 as a representative element, I guess is the way to say it, is not in this intersection. Neither is the equivalence class for the representative 0. That is not in the intersection, but everything else is. So we have K1 and K2, which are defined by these, which is just rewriting these inverse maps, so it's a little bit cleaner, the notation is a little bit less bulky. And so we now know this is a topological manifold because we have this atlas working just fine. And now the only problem is it differentiable? So we have to sort of study this transition function. And we're just going to study this one transition function. The other, of course, is symmetric. So what are the regions that are actually sort of eligible for all of this to work? Well, K1 operating on U1 intersection U2, right, which in other notations and in other books, if you use it, it will end up looking like U12. Sometimes that's the way they call it. They would call this U12. What is that going to look like in this set? So K1 is I'm taking this intersection, this bulk intersection, I'm pushing it back up here. What do I get up here? And the answer is, if you just sort of look at how that map works, you get this. Let me put in 0, right? And you will get a representative of, let's go back here, like that, at -1, and then you'll get this at 1. But remember, the intersection this intersection here does not contain 1, right? So that's why these are dotted lines. I make them curved because I'm kind of capturing an interval, but it's obviously really straight. And it doesn't have 0 in it either. So I've got to get rid of this, right? Because if you don't have 0, you don't have, remember the points are A, B, right? And if I'm getting rid of 0, right, so 0 is not in, I'm getting rid of 0 and all the B's associated with 0 too. So I'm actually getting rid of this whole line here, right? That's out. So the way I could kind of show that maybe is I would just maybe draw, emphasize that that is out, right? So what ultimately ends up happening is this chart map of this intersection region goes to this open-ended region here that doesn't contain -1 or 1, but it also doesn't contain 0, right? It doesn't contain 0 or the line above and below 0. So it's disconnected, and that's why I kind of wanted to write it with a gap. This region is disconnected from that region. There's no continuous way of, or there's no smooth way, continuous and smooth are heavy terms, but there's no way of starting here and with a path connecting to there. This is not path connected. It's not connected at all. So you have two disconnected regions, but that still doesn't matter. That is still the, just because it's disconnected doesn't mean anything too serious, right? We still have the this region, U1 intersection U2, under this chart mapping. This is what you get back here in R2. Likewise, down below, you will have sort of the similar situation. At 0, you won't have 0, and you won't have 2 pi, or I guess that would be, you won't have 0 and you won't have 2, but also you won't have 1, right? You won't have 1. So this is also a disconnected region. So that's under K2. So that would be K2 of U1 intersection U2, for what it's worth. Okay, so the reason that's important is because now we need to start thinking about this function here, right? So K inverse at, hey, whoops, sorry about that. My battery died, so there's probably an abrupt little jerk in the presentation here. So like where we left off is we were going to start, where I left off before my battery died, that is we're studying this thing. I think before we do that, why don't we make a quick connection of all this to our sort of our classic picture of a manifold, right? So the manifold classic picture was, well, maybe I'll do it on a slightly, no, this is a good spot. So remember the classic picture, we would have a region U1 and a region U2, and then a region U12, and then we would map it with one mapping into Euclidean space, right? And we would map it, the intersection region, with another mapping into Euclidean space. And this intersection region here would map to, say, like that, and this intersection, and under gamma 2 it would intersect to that. And we're now interested in the connection, these connections, for example, gamma 1 inverse, gamma 2 after gamma 1 inverse, right? So this picture here is whoops, this picture here is the sort of canonical manifold picture. And that is what we've got going on right over here, right? This U1, U2, although in the typical picture in the manifold we have this minor, or this relatively small overlap region. We've noticed that in some of the manifolds we've used, for example, the stereographic projection, and in this case too, these overlap regions are huge, except for maybe 2 points, right? In the stereographic projection, it was the poles, but here it's something similar. The 2 points are just these equivalence classes, because remember, every element of X is an equivalence class. So we're missing this equivalence class and this equivalence class, which is just 2 sets, right? Which really amount to 2 points. And this thing is, but this overlap region goes up here, and K1 on the intersection is everything I've gotten in green up here. That would be, for example, this here, right? So this this region in R2 corresponds to sort of this region right here in our abstract discussion of manifolds. Likewise, this region here corresponds to the mapping here, and that's what these are. K1 U1 intersection U2 would be gamma 2 of U12, gamma 1 of U12. Whoops, that's not right. Hold on. This green region here would be gamma 2 of U12, and this green region here would be gamma 1 of U12 under this picture here. So in our case, that's what these regions are, right? And all of this space here that's not part of that intersection, well, that is just this line here and 1, and this line here and 0, and 2, and -1, right? So, like we said, there's far more overlapping in these real circumstances typically, or the ones we've looked at, than in this abstract picture. Okay, so with that in mind, let me get rid of this. Well, I didn't fully get rid of it, did I? And now, so let's talk about this mapping. So what is it actually showing us? Let's see, I'm going to move this like this, and just to get these things out of the way, I'm going to select this and just move it over here for now. And we're going to now look at how this connects, right? So imagine you're a point over here on the left side, right? So in this case, if I took this, I guess is S. If the points are S and T, like we've been doing, this is S less than 0, and this is S greater than 0. So you'll notice that, so to map from S less than 0 from here to here, right? We'll have to find a point here that is in the equivalence class of these points that are less than 0, which would hang out normally here, but that's not part of this thing. But there is a representative here that matches that, and it's the point that, for example, if you had this point here, it would be this point here, shifted over by 2 pi. Oh, whoops! That's not. I'm not shifting it right. Maybe it's easier to start with these. The points that are in S greater than 0, this region is actually shared by this region. So this mapping for all the points in S greater than 0 is just the identity map, right? Because from this region here to here, it's all the same. It doesn't include 0, just like that, and it doesn't include 1, just like that. So the mapping from this disconnected region of this subset, that just goes directly through the identity map. So we can actually just assert that that's the identity map, right, between this region here and this region here. The problem is these guys over here, right, they have to be shifted to get into this region here. We have to shift them by 2 pi, right? We have to go 1 pi to get in this region and 1 pi over here, and you can only shift in 2 pi's, right? So we need to give it the S plus 2 pi minus 1 to the 1 t, right? So this point has to shift under this rule, whereas this one doesn't have to shift at all. It just goes to st, which is basically k equals 0, right? The -1 to the 0 and s plus 0 times 2 pi k. But this one has to shift by 1. So this one is going to end up actually swapping out t when it goes to get mapped over here. But so the function this function here that takes this region to this region has 2 different parts, right? But that's fine. Functions can have 2 different parts. One part is the identity, and the other part is the opposite of the identity. So it's like -1, right? It's basically -1 times everything. Well, so t is certainly -1. So this manifold, that's the transition function, and the transition function going the other way is similarly calculated. It's sort of the same thing. So this is the transition functions, and the point is that these are differentiable, right? The identity is certainly differentiable, and this is differentiable also. So this is actually a differentiable manifold, which is what we were actually trying to prove. So we have proved that the Mobius strip, as defined by this object, x, is a differentiable manifold. I think it's probably important to talk just a little bit more about how this function is actually structured. It's a bit confusing with these arrows going in two different directions. K inverse, remember, we're taking this intersection here, and under K1 inverse, it lands in this region here. And so it actually goes from here into this region. And under K1, it would go from here into this region. Under the inverse, this region here goes to an equivalence class. But that equivalence class is mostly shared by this one here. So when I project through K2, I land in this region here. The problem is that these points are treated slightly differently than these points, because ultimately these are functions that are restricted. This is where we lose. Remember, K2 is P restricted to V2 inverse, right? So when this lands in an equivalence class here, it gets pulled out and put into a different representative of the same equivalence class, but inside this region. So if I start here in this section where s is less than 0, I land in the equivalence class of, let's say I would land in -1/2, right? The -1/2 equivalence class. But when I project, and that's in that equivalence class, if I just inverse mapped it under P, I would end up with a point everywhere shifted by 2 pi. So I'd end up at -1. I'd end up here. I'd end up here. I'd have all those points under the inverse projection. I guess I should write, that should be the inverse projection, right? Right, if I did the inverse projection of this equivalence class, I would get all of these points separated by 2 pi. But now, so that's K1 inverse. I take this point, I do K1 inverse, I land in that equivalence class. But now, I come out of that equivalence class with P inverse restricted to V2, which is what K2 is. So restricted to V2, I have to land inside this thing we called U2, right? I have to land in here. So I need to find the representative of the -1/2 equivalence class that lives in here, right? Well, the -1/2 equivalence class that lives in here, that's where -1/2 is. So I have to add 2 pi. So I have to end up there, right? I have to end up there. So the one that's equivalent to that is going to be this point, because it's got to flip the sign. In order to stay in the equivalence class, it has to flip the sign of t. So that's why we introduced the -1, which on the t side, and that's why we end up with this -1 here. And likewise, on this side, if I take one of these points, say 1/2, so say I did the equivalence class for 1/2, this point at 1/2 gets dumped by K1 inverse into this point, the set that contains the equivalence class of 1/2. But then restricted to V2, well, that's already in there. That's easy. I just put it right here at 1/2. And I don't flip the sign, because it's actually, these sets overlap in this point, and it's actually 1/2 again. So it actually lands right here at 1/2, and I guess if I had picked it to be, say, 1/2 right there, it would end up in the same spot, because the class representative of 1/2, the only class representative of 1/2 in this region is in fact 1/2, just like it was here. The problem is over here, where we had -1/2 for A and some value of t, the representative of that was 2 pi advanced and a flipped sign on t, right? So that's where this -1 comes from. Oh, and by the way, I mentioned some things about the structure group, and that was a bit silly, right? This is not, as we've depicted, this is not a fiber bundle, right? This is a differentiable manifold. And you'll see these things are similar in many ways, but I already confused myself, right? The fact that these things are part of a structure group is not logical in the context of a differentiable manifold. I need to reformulate all this to make it look like a fiber bundle, and then I can talk about the structure group. So disregard what I said about the structure group. I should throw an annotation in that when I was trying. It's easy to get confused with these things. These things all look very similar. So the next step would be to show that this is a fiber bundle. And we'll probably do that in the next lecture, as we'll talk about the Mobius strip as a fiber bundle. It's actually a little simpler. This is very rigorous, what we've done here. And the reason is I just wanted to kind of walk the full picture through from start to finish, especially with the idea of, let's see, do I have it here? No, I guess. Especially showing how this marries up with our classic picture of differentiable manifolds that we always draw that looks like this, right? And we've actually done all that, right? We've done all that, right? Where we have these gammas, and this is literally that step by step. The complication, of course, is that in this particular case we end up with this disconnected set. So if we were to do this in this abstract notation, I guess it would look like this. You would end up with that and that. But but those are still legitimate regions, right? And gamma 1 inverse, or gamma 2 after gamma 1 inverse, will still map these disconnected regions to each other. And that's okay. That's fine. It's just a little bit of a twist on how this would look, but it's still completely legit. This abstract form is just very, very general and necessarily incomplete. Okay, so there's the Mobius strip. And again, what we didn't show was that this was literally the Mobius strip here, or maybe I should go back to the beginning, that this set, this equivalence class, and that this quotient space is literally homeomorphic to a parameterization of the Mobius strip sitting in R3 like we did for the cylinder. But I don't think we would learn too much by going through that. But this is your formal definition of what the Mobius strip is. So anything homeomorphic to this set can be called a Mobius strip. And there's a lot of interesting, important facts about this strip regarding surfaces, because it has to do with non-orientability. Mobius strip is, in any surface, is going to be non-orientable if there's a subset of that surface that is homeomorphic to a Mobius strip. And so looking for Mobius strips in surfaces is actually a very big deal. Anyway, so I think our next lecture we'll go back to fiber bundles, maybe talk about the Mobius strip as a fiber bundle quickly, and then move on.